Now let's talk about the general proof for the work kinetic energy theorem. If, let's suppose we have a box and a force pushes it across a frictionless floor a distance delta x, and if we suppose that v1 is the speed of the box before the push and v2 is the speed of the box after the push, like that, we can say that if f is a constant, the acceleration of this object will also be constant. For constant acceleration, we know equations of motions and we know how to solve them. So I'm going to suppose that I'm choosing equation number 3 in order to solve this. So equation 3 says v2 squared minus v1 squared equals 2a delta x. So I can manipulate this slightly. If I multiply both sides by a half m, I get 1/2 mv squared minus 1/2 mv1 squared equals ma delta x. Now if I was to look at this equation very carefully, what is ma? Absolutely. ma is actually F, which is the force that we are applying here. So this becomes 1/2 mv squared minus 1/2 mv1 squared equals F delta x. What is F delta x now? Absolutely. It is the work. So in other words, this above expression can be written as 1/2 mv squared minus 1/2 mv1 squared equals work. This is what is known as work kinetic energy theorem. So we will now have that the net work that is done by the object equals one, or the net force on the particle of mass m is equals to 1/2 mvf squared minus 1/2 mvi squared. This quantity, 1/2 mv squared, is what we are going to call kinetic energy. So if it has a final velocity associated with it, then we are going to call it kinetic energy final. And if it's the initial one, then we're going to call it initial kinetic energy. Note the kinetic energy of the object is due to the motion of the object, okay? And in other words, this W net or work net can also be the rate, the change in kinetic energy of an object is equals to the work done, okay? The kinetic energy is a scalar quantity. It is not a vector, it is not directionally dependent, and it has the same units as work or joules, okay? So when the work is done on a system, the only change on the system is its speed. The work done by a net force equals the change in kinetic energy of the system. Important to note is work kinetic energy applies in all situations, even when the force is a varying force. Okay? The change in kinetic energy is one possible result of doing work is to transfer energy to the system. If the work done on a particle is positive, its speed and hence its kinetic energy increases. If the work done on a particle is negative, its speed and also hence its kinetic energy decreases. So let's do a problem. One method to determine the kinetic energy of neutrons in a beam is to measure how long it takes the particle in the beam to pass between two fixed points known as a known distance apart. This is called the time of flight method. If the neutrons travel a distance of 6.2 meters in 160 microseconds, what is its kinetic energy? The mass of the neutron is given as 1.6 times 10 to the minus 27 kilograms. So our time of flight is what we need to solve for. Okay? And it says we need to find the kinetic energy of the beam of particles. So we know kinetic energy is equals to half mv squared, and the mass of the neutrons is given as 1.67 times 10 to the minus 27 kilogram, and we do not know its velocity. So if we only were able to find the velocity, we could calculate what the kinetic energy is. So what does it give us? We know velocity equals distance over time, right? So it gives us a distance that it moves. It moves 6.2 meters, and it says it moves at 160 microseconds. Now the question is, do we know what microseconds is? The answer is absolutely. We know this is going to be 160 times 10 to the minus 6 seconds, right? So I'm going to leave it up to you to plug into your calculators, and you will get kinetic energy in meters per second. Then all you have to do is take this number, plug it in here, take this number, plug it in here, and you can solve for kinetic energy, which is going to be kilograms, meters per second, and these become equals to a particular unit that we just talked about, and you can find what that should be. Sorry, this should be meters squared per second squared. Example 2. A block of mass m, 3.63 kilograms, slides on a horizontal frictionless table with a speed of 1.22 meters per second. It is brought to rest by compressing a spring in its path. By how much is the spring compressed if the force constant K is 135 newtons per meters? So in this case, it gives us a block of mass m, which is equals to 3.63 kilograms. And it has a velocity of 1.22 meters per second, right? And it says that it is brought to rest, okay? So that's important. That means its final velocity equals 0 meters per second. It is brought to rest by means of compressing a string. So this is what the picture looks like. So remember, this is how basically trains are stopped. They have a spring attached to it, so when a train comes, it hits it, it compresses the spring, and it stops it. And it also gives me the spring constant, which is equals to, if I am reading this correctly, 135 newtons per meters, right? So velocity, it has a velocity, it has a final velocity. Now, how am I going to solve it? I need to find, first of all, I need to know by how much is the spring compressed, okay? So I need to find delta x for the compression of this spring, okay? That's what I need to find. I know that when a spring is compressed, the work done by the spring is equals to 1/2 k d squared, or k delta x squared, right? This is the amount of work I have. Now all I have to do, this is given, is somehow find the work done and plug it into this expression and solve, okay? What do I know? I know the work kinetic energy theorem. That's going to be useful. What was it? Work kinetic energy theorem said work net is equals to the change in kinetic energy, which means kinetic energy final minus kinetic energy initial, right? Sorry, this should be a half here, okay? So if I was to take this, and I know that kinetic energy is 1/2 mvf squared minus 1/2 mvi squared. Note, I don't put an f for masses because this is just ordinary everyday life, right? And so the masses should not change as they go from one to another. It said to me that it comes to rest, so this means vf goes to 0. And I will have 1/2 mvi squared, right? So work net is actually equals to 1/2 mv squared. Aha! Now this is the value I can plug into here. That means I will have 1/2 mvi squared with a minus sign equals 1/2 k delta x squared. Now do I have all the values that I'm going to need? The half goes away, the minus goes away, right? I have mvi squared equals k delta x squared, right? So I have m, I have v, I have k, I can solve for delta x. And I'm going to leave that up to you guys to solve.